Hi Rebecca, I'm trying to learn particle physics. Today the symmetry of a standard model, and after we've done that we're gonna do morning stretching. And if you participate in the morning stretching, then it's that at your own risk. Now, we already read that part about the symmetry of a standard model. We didn't really understand it all, but we will continue in particle physics somewhere else. But we had here something about Minerva, a little biography or whatever that is. And I'm going to do it in another course, not in particle physics, doing on with that. We did it as an overview because I think it's important to know it in particle physics, but to go more in detail and to learn it more properly, we will do it in another course. And also the quote of Hellman Whale about her, we will do in another course, quotology. But I want to say in these two courses, very short, what is it what she said? And now we're here and trying to find out in this text, what do we know about what she said about the symmetry of a standard model? Einstein's work revolutionized our view of the universe, but also spurred a great deal of interest in the role of symmetries in physical laws. The person who made something concrete and mathematical out of that was one of the greatest unsung heroines of modern physics, Minerva, who formulated the theorem that today bears her name. Simply stated, it says that symmetries lead to conservation laws. That means because I didn't really get it, but we want to go on where we get it. This formalized an idea intrinsic to, but unstated in, the two theories of gravity. For another example, consider a puck placed on a very smooth, very large frozen lake. When the puck slides, the lake is the same. Nova's theorem provides a general way of turning that statement of symmetry into a conservation law. The symmetry is that the lake stays the same. I don't really get the idea why it is a symmetry. Conservation laws are the bread and butter of physics, mathematical shortcuts that allow us to compute physical quantities once and never again. Maybe I explain it just with an example. But the lake stays completely independent whether there's a puck on the ice or not. And that makes it possible to calculate a thing once, and then it is not necessary to calculate it again. Whatever you start with, that is what you will end up with. This is incredibly useful. Think how much trickier it would be if the number of hours in the day changed constantly and wasn't conserved in 24. It is bad enough twice in the year when the clocks go forward or back. Most of the great laws of physics include some statements of conversation, implicitly or explicitly. Before Nerva, energy was simply presumed to be conserved, an assumption so basic that it became known in the 19th century as the first law of thermodynamics. But due to the mathematics associated with Nerva's theorem, it becomes plain that energy is conserved because of an even more basic symmetry, specifically that the laws of physics aren't changing with time. What Nerva's theorem adds up to is a practical prescription for making progress in physics. Identify symmetry in the world's workings and the associated conservation. Law will allow you to start meaningful calculation. Okay, maybe we can say that. Find the symmetry. What is meant with that? Is that the meaning that if on one lake, the lake stays conserved, also with every other lake it's the same? Is that the symmetry? Now you have to just find out how it is conserved and you can calculate the other lake. I don't really get it yet. The universe has no up or down, nor center for that matter. Its laws don't seem to be in any way related to where we measure them, how our measuring devices are pointed, or even when we decide to make the measurements. For Noether's theorem, symmetries of space and time yield conservation of energy, momentum and angular momentum everywhere, all the time. I don't really understand the word symmetry. What symmetry? Does it mean if it's here like that or that lake, the other lake has it the same? Symmetry of space and time. Yield conservation of energy, momentum and angular momentum everywhere. But there's much more. Symmetries in space and time might be obvious to the naked eye, yet Noether's theorem's true strength comes from internal symmetries. To the uninitiated, the standard model of particle physics is nothing more than a list of fundamental forces and particles, but it is a model of internal symmetries writ large, and it was built on Noether's theorem. Because one atom is the same as in the other one. The most familiar force dealt with is the electromagnetism. Noether's theorem shows that charge conservation too arises from symmetry. Fundamental particles have a property called spin, just the position doesn't matter on a frozen lake, which is known as the spin's phase, doesn't change physical calculations. What pops out, according to Noether's mathematics, is charge conservation. Hermann Weyl took this idea of phase symmetry a step further and supposed that every electron might be twisted by a different amount and still remain the same. As the standard model has developed, so the symmetries of interest have become more subtle, but Noether's theorem has been the gift that keeps on giving. It is hard to conceive, for example, that electrons, particles that run through wires to power electrons and neutrinos, which fly through us by trillions every second without leaving a mark, are in some sense the same particle. The weak force is indifferent to whether a particle is an electron or neutrino. Switch them round and weak interactions will be the same. This symmetry produces this symmetry. I don't really understand what symmetry. The word symmetry. If something is symmetrical, that means on the other side it looks the same. Basically, humans are symmetrical on one side or the other. The weak force is indifferent to whether a particle is an electron or a neutrino. But some things act the same, no matter where they are. The force acting on the neutrinos is the same as acting on the electrons. Physics is still far away from a final resolution, but in the thrill of a chase for better answers, it is studying symmetries that will guide us along the way. It is Noether's theorem that allows us to make use of that allows us to magic useful physical insights from that. Can't really get it yet. Maybe here? I think we're pretty close. Maybe we even have it, but if we don't have it, I want to say it wrong. Now, it could. I think it's one of the 2 or 3 things which I said, but I'm not really able to say them now, and I don't have the time now. Now we will continue with particle physics in the next part of whatever we will do with that part in the other 2 courses. We will continue with particle physics in the next part. We will do now the morning stretching. If you stay here and participate in the morning stretching, then that is at your own risk. Go to stable stance, and we're doing forward shoulder circles. We come back, up, and front, and down. backwards. And now breathe in with your shoulders up. And breathe out, let me fall down. Again, in with shoulders up. Out with shoulders down. Again in. Out. Last time. And out. Now we're doing the upper plank. Breathe in, lift the arms up. And reach high always with one arm. And imitate taking an apple, hanging high on an apple branch, to turn it a bit around and to plug it. Now we're doing the shift down. Arms up to a T, legs wide apart, breathe in. And out we're going over to one side, just with the upper part of the body. Breathe again in. And out over to the first side, to the second side. Again in. Out. Again in. Out. Again in. And out, we're leaning onto our knees, the buffalo fighting its hangover. Breathe again in. And out, one shoulder front. In the shoulder back. And out, shoulder front. In the shoulder back. Out, shoulder in front. In the shoulder back. And out the last time, shoulder in front. In. And out and hanging down. We only have to come deeper down by breathing deep in into the nose. And we're breathing out from the mouth. Again in. And out. Again in. And out over to the first leg. Breathe again in. And put over to the other leg. Again in. Out into the middle. Breathe again in. And out we're coming slowly with the round back up and moving to top backwards, shoulder to shoulder. Now we're toes pointing to the outside. We're having an unleft space between the heels. Breathe in, lift the arms up. And breathe out and we're going down. Place your elbows against the inside of the knees. Breathe in, straighten up the back. And breathe out, we're coming up with the back. Breathe again in. And out, again down. Again in, straighten up the back. Out and again. Again in. Out into the middle. Breathe in, straighten up the back. Breathe out and come slowly up in one straight line. Now we're doing the seahorse pose. Hand with standing leg, the other heel on top of the standing leg. Breathe in. Do this only if you can do it without to injure yourself, and breathe out and go slowly down. Einstein's work revolutionized our idea of a universe, but also spurred a great deal of interest in the role of symmetries and physical laws. The person who made something concrete and mathematical out of that was one of the greatest unsung heroines of modern physics, the changing of the leg. Minerva was who formulated the theorem that today bears her name. Simply stated, it says that symmetries lead to conversation laws. It leads to conversation. Because there's a symmetry, the force acts here the same as there, and that leads to having the state all the time. I don't really get it now with the leg example. And you're coming up again. This formula is the intrinsic to, but unstated in, the two theories of gravity. For another example, consider a plug placed on a very smooth, very large frozen lake. Whether the plug slides, the lake is the same. Minerva's theorem provides a general way of turning that statement of symmetry into a conversation law. As exercise, legs wide apart, we're breathing in. And out. In. Out. In. Out. out, breathe and cross the legs, and out. That was morning stretching. I thank you very much. I don't feel